Good morning, I'm Manuel Zarzo. We are in Unit 8, Regression, and today in this video I will talk about covariance and correlation coefficient. Okay, well, so how can we quantify the degree of correlation between two variables? We have this formula, the formula for the covariance. This is the formula, so this is the sum of every value minus the average of the x multiplied by every value of the y minus the average of the y, and everything divided by n minus 1. Okay, and now I'm going to explain this formula. N is the number of pairs of values, so number of individuals. Good. Okay, so here we can see that we have a negative correlation. When the temperature increases, the consumption for heating decreases. Okay, so here we have like a cloud of points that goes down with a negative slope. Okay, so now first we can see that we can fit a straight line with a negative slope, and then we have the average of the x, and then we have the average of the y. Now, so let's consider a point here in this position, like this one. Okay, so now we have that the y for this point minus the average of the y is negative, but the x minus the average of the x is positive. So if we multiply a negative value by a positive value, this product is negative. Okay, but the same occurs here. For all points here in this quadrant, if we make this operation, it becomes negative. Okay. But for this quadrant, the few points in this quadrant, that operation becomes in a positive covariance. And here, for the points in this quadrant, which are a few points, that operation becomes also positive. Okay, so we can see that most of the points are in this quadrant with produce a negative value, and most of the points are here which produce a negative value. So at the end, if we compute the covariance, it will become negative. Okay, so the idea is the following. If we can fit a straight line for a cloud of points, if the slope is negative, okay, b is the slope of this line, of this fitted line. If the slope is negative, the covariance will be negative, and if the slope is positive, the covariance will be positive. And if the slope is 0, okay, if there is no trend, the covariance will be 0. And this is the expression of the covariance by using expectation. Okay, so here the formula is when we have a discrete set of points and pairs of values, but if we have like an infinite amount of points, so we should apply mathematical expectation, and this is the formula that we should apply. Okay, now let's imagine that we have an example with a covariance of minus 50. So is the correlation between the two variables weak or strong? Well, okay, well, the drawback, so we cannot answer this question. We cannot know if the correlation, the degree of correlation is weak or strong. So the drawback of the covariance is that it depends on the units. It depends on the scale in which the variables have been measured. So then there's a need to develop or to use another coefficient, which is called correlation coefficient. It was developed by Pearson, so sometimes it's called Pearson's correlation coefficient. The formula is the following. It's usually called as R. R is the usual way, the notation that we usually apply for this correlation. It's the covariance divided by the product of the standard deviations. So we divide the covariance by the standard deviation of x multiplied by the standard deviation of the y. This is a sample level. Okay, so if we the formula, the equivalent formula at the population level is this. So instead of R, it's called rho. Okay, the Greek letter equivalent to the R. Remember that usually in statistics we reserve the Greek letters for the coefficients at the population level. Okay, so if this correlation is 0, it means that there is no linear relationship between x and the y. And if this coefficient is exactly 1 or minus 1, it implies that there is an exact linear relationship between the x and the y. Okay, so one advantage of this coefficient is that it is limited between the range of minus 1 to 1. Okay, so if it is close to 0, it means that there is no relationship but it is close to 1 or -1, it means that there is a strong relationship. Okay, so the advantage is that it's non-dimensional. So if we change the units of x and y, so the result is the same. Okay, now we have what is called the matrix of variances covariances. Okay, so if we have just two variables, x1 and x2, so the first element of this matrix will be the covariance between x1 and x1, the second, the covariance between x1 and x2, x2, x1, x2, x2. Okay, so all the elements of this matrix correspond to the all possible combinations of the covariance between the pairs of variables. Okay, but what happens? What is the covariance of x1 with respect to x1? Okay, well, so if we take the formula, this one, based on the mathematical expectation, x1, x versus x, okay, so this is the mathematical expectation of x minus the average multiplied by x minus the average, so it's the same. So this is squares. So we just can see that it is the variance of the x. Okay? And the same can be demonstrated using the formula for a discrete set of values. So, important result. The covariance of one variable with respect to itself is the variance of that variable. So, this matrix, where all elements are covariances, this is why this matrix can be called matrix of covariances, becomes a matrix where the elements of the main diagonal are the variances. Okay, so this is why this matrix has like two possible names. It can be called matrix of covariances or matrix of variances covariances, because the elements in the main diagonal are the variances and the elements out of the main diagonal are the covariances. It's okay. For example, in case we have like three variables, okay, this is all pairs of possible combination of the of those three variables. So these are the all possible covariances, and then it becomes that the matrix is symmetric. Okay, why? Because the covariance of x1 versus x2 is the same as the covariance of x2 versus x1. So this element and this is the same, and this the same as this one, and this element is the same as this one. So the matrix is symmetric. Okay, so we have also another matrix called the matrix of correlation. So it's the same, but instead of covariance, here we have the correlation coefficient. Okay, so that would be the correlation coefficient of x versus x, x versus y, the y versus x, and the y versus y. Okay, so it becomes that the correlation coefficient of one variable versus itself is always 1. Okay, so here all elements in this diagonal are 1, and so this does not provide any kind of information. And for that reason, for example, star graphics leaves the values in this main diagonal as like blank, empty, because the information is useless. It's like trivial. Okay. Now, what is the bivariate normal distribution? Okay, so in previous videos, I explained about the normal distribution, the theoretical model about the normal distribution of one single variable. But also we can talk about the normal distribution of two variables that vary together, okay, that can also have correlation between them. Okay, this is what we call bivariate normal distribution. So how many parameters do we need to define this kind of model? Okay, so well, we need a vector of means. Okay, so we need the average of the x, the average of the y, or the average of the first variable, the average of the second variable. Okay, and also we need the matrix of variances covariances. Okay, so we need the variance of the first, the variance of the second, and then the covariance of between them. So this is another notation that you can find in some books. The covariance between two variables sometimes is represented as sigma square and using as subindex 1, 2. Okay, but I prefer this kind of notation. I prefer to write cov, like covariance. I think like it's more clear, but anyway, just for your information, in some books you can find this notation. Okay, so the two components, x1 and x2 of a bivariate random variable follow a normal bivariate normal distribution if the joint density function is the following. Okay, remember that when I explained the normal model, I presented the mathematical equation of the density function. Well, good. Now also there's a density function for this bivariate normal distribution, which is the following. Well, the equation is very complex, so I'm not going to explain in detail this equation, but I think it's interesting to count how many parameters are necessary to define this function. Okay, well, so here we have m1 and m2, okay, the average of the first variable at the population level, the average of the second. Also here we have the variances, the variance of the first, the variance of the second, and also we need the correlation coefficient, okay, the correlation coefficient between them. So in total we need 1, 2, 3, 4, and 5. So we need 5 parameters to define this kind of model. But the advantage is that based on this density function, we can integrate, okay, we can solve the double integration and make calculations of probability. So you know that there is no primitive of this function, but using numerical methods, okay, so we can program an algorithm able to make this kind of calculation. Good. This is the shape of the density function in a three-dimensional space. In this case, the average of the x is 0, the average of the y is also 0, the variance of both variables is 1, which implies that most variables are comprised between -3 and 3, the y is the same, between -3 and 3, and in this case the correlation is 0, okay, the correlation is 0. Well, so it can be represented like this way. So bivariate normal distribution with a vector of means equal to 0, and this matrix of variances covariances equal to the identity. Well, so the volume below this curve or this surface is 1, okay, and then probabilities are obtained by integration, as I have mentioned in the previous slide. Well, so if we make horizontal planes, so if we cut this volume by using horizontal planes, it becomes this kind of figure, which is called isodensity curves. Okay? It's equivalent to this picture that we are more familiar in statistics. So it's like a cloud of points without any trend. Okay, so when the x increases, the y does not increase nor decrease. So there is any trend. So, and then we can see that most of the data are comprised like within this space, and this is what we represent here, that most of the data are comprised here. Okay, this is another example. Here we have that the average of the first is 5, the average of the y is 7. You can see it here, 5 and 7. Now the variance of the x and the y is 1, okay, but there is a covariance. The covariance between them is 0.85, so there is a positive relationship between them. So now if we cut by using horizontal planes, this is what we have, okay. Now we can see a trend, a very clear trend. When the x increases, the y also increases. So here we see that there is positive correlation. Okay, here I finished this first this video about covariance and correlation coefficient.